When something travels between the stars and enters our solar system, we expect it to follow certain rules. Gravity dictates the path. The sun's pull determines the trajectory. And then there's 3I Atlas, an object that appears to be rewriting those rules in real time. Right now, as we speak in early January 2026, this interstellar visitor is making its way through the outer reaches of our solar system. It's been roughly 8,000 years since 3I Atlas entered the Oort cloud, that vast spherical shell of icy objects at approximately 100,000 astronomical units from the Sun. That's 15 trillion kilometers from our star, a distance so vast that light itself takes more than a year and a half to traverse it. For those 8,000 years, 3I Atlas has been falling toward the Sun. But now it has reached the turning point, embarking on the second half of its journey, heading back out into the cosmic void. This is where things get interesting, and if you want to follow this story as it unfolds over the next few months, I'd recommend hitting that subscribe button, because what happens next might fundamentally change how we think about visitors from beyond our solar system. Let's look closer at the data, because there's something deeply unusual about 3I Atlas. When astronomers track objects in space, they use sophisticated mathematical models based on gravitational physics. These models are extraordinarily precise. We can predict where a comet will be years in advance. The math works. It always has. Except with 3I Atlas, it doesn't quite work. The object exhibits what scientists call non-gravitational acceleration. Something else is providing an extra push, nudging it off the path that pure gravitational dynamics would predict. Non-gravitational acceleration isn't entirely unprecedented. When comets approach the Sun, ice sublimates into gas and jets outward, creating a rocket effect. But 3I Atlas has traveled so far from the Sun, through regions so cold, that this explanation becomes difficult to justify. Out in the Oort cloud, temperatures hover just above absolute zero. Ice doesn't sublimate vigorously enough under these conditions to produce measurable acceleration. Here is the crucial detail. The non-gravitational acceleration of 3I Atlas has been persistent enough that it must be included in any forecast of where the object will be. This isn't a minor correction. Without accounting for this mysterious push, our predictions would be off by millions of kilometers. So, what does this actually mean? We're watching an object that behaves unlike the comets we know. Either our understanding of outgassing in extreme cold is incomplete, or we're dealing with something that doesn't fit into our existing categories. The designation 3I stands for Third Interstellar Object. The first was Oumuamua in 2017. The second was 2I Borisov in 2019. But where 2I Borisov acted like a conventional comet with a visible tail and predictable behavior, 3I Atlas has been different from the start. The object was detected by the Atlas Survey System, a network of telescopes scanning for potentially hazardous asteroids. When astronomers calculated its orbit, they immediately recognized the hyperbolic trajectory, the signature of an object not bound to our Sun. The excitement was immediate. Here was another messenger from interstellar space. But as observations accumulated, that non-gravitational acceleration kept showing up. It wasn't measurement error. It was real, persistent, and unexplained. And now, as 3I Atlas heads back toward the outer solar system, it's not drifting into obscurity. It's heading toward an appointment with Jupiter, an encounter so close and so precisely timed that it has scientists worldwide checking their calculations. This contradicts what we previously thought about random encounters in the solar system. The odds of such a close approach, given the object's trajectory and timing, are astronomically small. Yet, here we are, watching it unfold. The stage is set, and we're about to see whether this comet that doesn't act like one has any more surprises in store for us. Building on this unusual acceleration pattern, let's talk about what's going to happen on March 16th, 2026. That's just over 2 months from now, and the date has been circled on calendars at NASA, ESA, and observatories worldwide. On that day, 3I Atlas will pass within 53.61 million kilometers of Jupiter. That's about 140 times the Earth-Moon distance. In everyday terms, it's vast, but in planetary dynamics, this is extraordinarily close. Let's look closer at the data, because there's a number that should make everyone sit up. Jupiter has what astronomers call a Hill sphere, the region where the planet's gravity dominates over the Sun's tidal forces. For Jupiter, this Hill radius extends to approximately 53.5 million kilometers from the planet's center. Now compare that to 3I Atlas's closest approach, 53.61 million kilometers. The interstellar object will pass just 110,000 kilometers beyond Jupiter's Hill radius. That's a difference of roughly 0.2%. 3I Atlas is threading a needle skating along the edge of Jupiter's gravitational dominance. This is not how random encounters work. When an object comes from interstellar space on a hyperbolic trajectory, the odds of passing this close to any particular planet are vanishingly small. Yet here we have 3I Atlas, with its unexplained acceleration, arriving at Jupiter's doorstep with Swiss watch precision. But there's more. On March 17, 2026, 3I Atlas will pass within 30.46 million kilometers of a small moon called Eupheme. It's one of Jupiter's irregular satellites, discovered in 2003, just 2 kilometers across. This is a tiny captured rock, one of 95 known moons orbiting Jupiter. So, what does this actually mean? Why care about one obscure moon among dozens? The answer lies in the timing. Eupheme is part of the Ananke group, a family of 15 moons on highly elliptical orbits, circling Jupiter opposite the planet's rotation. These are captured objects, shattered remnants of larger bodies that Jupiter ensnared long ago. Eupheme's orbit takes 588 days to complete. Because it's so elliptical, the moon's distance from Jupiter varies dramatically. At its farthest point, Eupheme reaches 27.7 million kilometers from the planet. Here is the crucial detail. Eupheme will reach its apojove, its farthest point, on January 23, 2026. That's just 15 days from now, and 52 days after that, 3I Atlas will make its closest approach to this moon. When Eupheme is at its farthest point, it's in the most weakly bound part of its orbit, at the edge of Jupiter's influence, moving slowly in a configuration where dynamics are most delicate. And that's when 3I Atlas passes nearby. It's as if the interstellar visitor timed its arrival to coincide with Eupheme's most vulnerable moment. Now, let's acknowledge what astronomers would say. There are 95 moons around Jupiter. With that many objects, the probability that one would be in some interesting configuration is not that small. This is the cosmic coincidence defense. With enough moving parts, alignments happen by chance. This contradicts what we previously thought about interstellar objects, though. Oumuamua came and went without close planetary encounters. 2I Borisov also maintained safe distances. These were flyby events, brief glimpses we could study before they vanished. But 3I Atlas is different. It's engaging with the solar system in a way previous visitors didn't. That non-gravitational acceleration means its trajectory has been modified by forces we don't fully understand. And now it's arriving at Jupiter at a distance and time that puts it right at the threshold of gravitational capture dynamics. Here is the crucial detail that brings this together. When 3I Atlas passes Jupiter on March 16th, it will be moving at approximately 66 kilometers per second relative to the planet. That's nearly 240,000 kilometers per hour. It's fast, but not so fast that gravitational interactions become negligible. At that speed and distance, Jupiter's gravity will absolutely affect 3I Atlas, bending its trajectory, potentially stressing the object, creating conditions where interesting dynamics can occur. What kind of dynamics? What could actually happen? That's what we need to explore next, because the answer involves looking at how Jupiter acquired its family of 95 moons, and whether that family is about to get larger. If you're finding this fascinating, drop a comment below. What do you think is the most intriguing aspect? The timing? The unexplained acceleration? Let me know, because there's more to unpack. As we established with 3I Atlas's peculiar trajectory and timing, we're not dealing with a typical encounter. And to understand why this matters, we need to look more carefully at the target of this cosmic rendezvous. Given what we now understand about the March 16 encounter and the 53.61 million kilometer approach distance, we need to explore exactly what Eupheme is and why this 2-kilometer rock has become the focal point. Because when you dig into the details, you discover it's part of a much larger mystery involving planetary capture, catastrophic collisions, and the violent history of the outer solar system. Eupheme was discovered in 2003 by astronomers using the Mauna Kea observatories in Hawaii. With a mean diameter of just 2 kilometers and an albedo of about 0.04, this moon reflects very little sunlight. It's dark, small, and distant. Finding it required sophisticated cameras and patient analysis. But Eupheme didn't show up alone. It's part of the Ananke group, a family of 15 Jovian satellites sharing remarkably similar orbital characteristics. They all orbit Jupiter retrograde, opposite to the planet's rotation. They all have highly eccentric orbits inclined at steep angles. These are not orderly orbits from moons that formed in place. These are the chaotic orbits of captured objects. Let's look closer at the data on how these captures work. The prevailing theory is that the Ananke group formed from the breakup of a single, larger parent body. Sometime in the distant past, a wandering asteroid or comet passed too close to Jupiter. The planet's gravity captured it, pulling it into an unstable orbit. Then, through collision or tidal stresses, this parent body shattered. The largest fragment was named Ananke. The smaller pieces became the 14 other moons, including Eupheme. The retrograde orbits are key. The 4 large Galilean moons orbit prograde in Jupiter's equatorial plane. They formed from the disk that surrounded Jupiter billions of years ago. But Eupheme and its siblings orbit retrograde backwards. This strongly indicates they didn't form in place. They came from somewhere else and were captured. This contradicts what we previously thought about how common these captures are. Jupiter has 95 known moons, and the vast majority are small, irregular, captured objects like Eupheme. In 2000, we knew of about 17 Jovian moons. Today, 95. And there are likely many more waiting to be discovered, too faint for current telescopes. So, what does this actually mean for the 3I Atlas encounter? It means Jupiter is very good at capturing things. The planet's massive gravity creates opportunities for objects to be gravitationally ensnared. And the timing of 3I Atlas's approach, with Eupheme at its apojove just 52 days before closest passage, is starting to look less like random coincidence and more like an example of how these capture dynamics work. Here is the crucial detail. Eupheme's orbit takes it out to 27.7 million kilometers from Jupiter at apojove. That's well beyond the 30.46 million kilometers that 3I Atlas will be from Eupheme on March 17th. In other words, 3I Atlas will be passing through the region where Eupheme spends part of its orbit. The interstellar visitor is threading through the Ananke group's orbital territory. When two objects pass close in space, they exchange momentum. The gravitational interaction can alter both trajectories. Could 3I Atlas perturb Eupheme's orbit? Almost certainly, at least slightly. Given that Eupheme is already on a highly elliptical, loosely bound orbit, any perturbation could have long-term consequences. It might alter the orbital period, change eccentricity, or even destabilize the orbit entirely. But there's another possibility that's even more intriguing, the one that has astronomers preparing telescopes and spacecraft for intensive observations in March. What if 3I Atlas itself gets perturbed so that pieces of it end up in orbit around Jupiter? As we established with the 53.61 million kilometer approach distance, 3I Atlas will be just barely outside Jupiter's Hill radius. It's in a regime where capture is theoretically possible, and if the object were to fragment, if pieces broke off during the encounter, some could receive velocity kicks that put them into bound orbits around Jupiter. They could become new moons, additions to Jupiter's already extensive family. The question is, can a natural comet fragment in a way that produces the right velocity kicks? Can the physics of ice sublimation, tidal stresses, or internal structural failure generate debris moving at the speeds and directions necessary for Jupiter capture? Because if not, if natural breakup physics simply cannot produce the required conditions, then observing new moons after March 16th would tell us something profound about 3I Atlas. It would tell us the object is not entirely natural, that it has capabilities beyond what ice and rock can provide on their own. This connects to the non-gravitational acceleration we discussed at the beginning. An object that can accelerate itself in ways that gravity alone cannot explain might also be able to fragment in ways that natural objects cannot. And if we observe new Jovian satellites with orbital characteristics impossible to explain through conventional breakup mechanisms, we'll have moved from mystery to discovery. But we're getting ahead of ourselves. Before we can evaluate what might happen, we need to understand the physics constraints. We need to look at the numbers, the velocities, the energies involved, and determine what is and isn't possible for a natural comet in this scenario. That's where the analysis gets really interesting and where some scientists are starting to raise eyebrows. Building on this possibility of fragment capture, We now need to confront the physics directly. And this is where the mathematics become uncomfortable for anyone trying to explain 3I Atlas as a conventional natural object. Because when you calculate the velocity changes required for capture and compare them to what natural processes can produce, you run into a problem, a significant problem. Let's start with the relative velocity between 3I Atlas and Jupiter at closest approach. As we established earlier, this velocity is approximately 66 kilometers per second. At that speed, you could travel from New York to Los Angeles in about 60 seconds. But in cosmic terms, 66 kilometers per second is not particularly extreme for the outer solar system. Here is the crucial detail. For a fragment of 3I Atlas to become gravitationally bound to Jupiter, it needs to slow down until its speed drops below the local escape velocity. At a distance of 53.61 million kilometers from Jupiter, the escape velocity is approximately 2.2 kilometers per second. Anything moving slower than that cannot escape Jupiter's gravity. Now let's look closer at the data and do the math. The relative velocity is 66 kilometers per second. The escape velocity is 2.2 kilometers per second. For a fragment to transition from 66 km/s to less than 2.2 km/s, it needs a velocity change of at least 63.8 km per second in precisely the right direction. It's not enough to just slow down. The fragment needs to be kicked in a way that cancels most of its motion while leaving enough tangential velocity to maintain orbit rather than falling straight toward Jupiter. This is an exquisitely fine-tuned requirement. And this brings us to the central question. Can a natural breakup of a comet produce velocity kicks of 63.8 kilometers per second or greater? The answer, according to the physics, is no, and it's not even close. When a comet breaks apart through outgassing, the velocity of ejected material is limited by molecular speeds at comet temperatures. For water ice, this is measured in hundreds of meters per second, perhaps up to a kilometer per second at most. That's nowhere near 63.8 kilometers per second. It's off by a factor of more than 60. What about tidal breakup? Comet Shoemaker-Levy 9 was famously ripped into multiple pieces by Jupiter's tidal forces in 1994. But tidal breakup doesn't fling fragments away at high speed. It gently pulls them apart. The velocity differences are again on the order of meters to hundreds of meters per second, not tens of kilometers per second. So, what does this actually mean? Jupiter's surface escape velocity is 60 kilometers per second. Any breakup process on a much smaller body like a comet cannot impart velocities exceeding what a massive planet like Jupiter can generate. The energies involved in breaking up a kilometer-scale object simply cannot produce the velocities needed. This contradicts what we previously thought was even possible for natural objects in this scenario. The required velocity kick is 63.8 km/s, but natural breakup processes max out at a few km/s. The physics doesn't allow for a natural mechanism that could produce the required change. And there's another constraint. Remember that the escape velocity at 3I Atlas's closest approach is only 2.2 kilometers per second. The margin for error is incredibly small. The kick must precisely calibrate the fragment's velocity to something between 0 and 2.2 km/s. That's a tolerance of about 3%. In engineering terms, this is what we call exquisitely designed. Let's think about what this implies. If, on March 17, 2026, we observe a new moon around Jupiter that came from 3I Atlas, we'll have observed an outcome that natural physics says shouldn't be possible. The creation of a bound satellite from a high-speed interstellar encounter requires velocity changes that comets cannot produce through any known mechanism. That would constitute what some researchers are calling a technological signature. It would suggest that 3I Atlas can control its fragmentation, impart specific velocities to specific pieces, and execute maneuvers that natural physics does not allow. In short, it would be evidence of design. Now, let me be clear about what we're saying and what we're not saying. We're not claiming that 3I Atlas is artificial. What we're saying is that if we observe certain specific outcomes from the March encounter, those outcomes would be very difficult to explain using only natural processes. They would require new physics, or they would require us to consider possibilities that we've traditionally ruled out. If you're finding this analysis compelling, hit that like button. The more engagement this gets, the more people will see it, and the more pressure there will be for transparent analysis of whatever we observe in March. Public attention can be a powerful force for scientific accountability. As we prepare for the monitoring campaign and the potential discoveries ahead, we need to understand exactly what instruments we'll be watching and what the various possible outcomes might mean. Because depending on what happens on March 16th, our understanding of interstellar objects, planetary capture dynamics, and perhaps of our place in the universe could be about to change. Given what we now understand about the physics constraints and the implausibility of natural capture mechanisms, the question becomes, what exactly are we going to observe, and how? Because March 16, 2026 is not some distant hypothetical date. It's 67 days from now, and the astronomical community has already begun preparations for what might be the most closely watched planetary encounter in modern history. Let's start with the assets we have in position. The most important is NASA's Juno spacecraft, orbiting Jupiter since July 2016. Juno's suite of instruments includes cameras, spectrometers, and sensors capable of detecting and characterizing objects in the Jovian system. During the 3I Atlas encounter, Juno will be uniquely positioned to observe the event from close range, with resolution that ground-based telescopes cannot match. From Earth, the largest ground-based telescopes will also be tracking the encounter. The Atacama Large Millimeter Array in Chile, the Very Large Telescope, the Keck Observatory, and Subaru Telescope in Hawaii all will be pointed at Jupiter during the critical period. Coordination between observatories is essential to ensure continuous coverage and provide multiple independent data sets. Let's look closer at the data we'll be collecting. Optical observations will track 3I Atlas's position and brightness. Any fragmentation should produce brightness changes. Spectroscopy will analyze the composition of ejected material, looking for signatures of ice, rock, organic molecules, or potentially more exotic materials. Infrared observations will search for thermal emissions, and radar observations could provide direct ranging and velocity measurements. The critical observation is this. After March 17th, once 3I Atlas has passed Jupiter, will there be any new objects in orbit around Jupiter that weren't there before? This is the test that determines whether the physics we've discussed actually manifests. Discovering a 96th moon would be front-page news under any circumstances. But one that appeared immediately after an interstellar object passed through? That would be extraordinary. Here is the crucial detail. The detection of new satellites is not instantaneous. Even after fragments are released and enter bound orbits, it takes time to confirm their presence, calculate orbits, and rule out pre-existing objects that simply weren't noticed before. Distinguishing a genuinely new object requires multiple observations over days or weeks. So, we shouldn't expect definitive answers on March 17th. The analysis will unfold over subsequent weeks and months. But the waiting won't be passive. Every major telescope with access to Jupiter will be searching for changes in the satellite inventory. Amateur astronomers with advanced equipment will participate as well. The data will be public, or at least accessible to the scientific community, making independent verification possible. For a claim as significant as detecting a technological signature, multiple independent confirmations are essential. So, what does this actually mean for the broader search for extraterrestrial intelligence? Traditional SETI has focused on radio signals, optical pulses, or electromagnetic signatures from distant civilizations. But in recent years, there's been growing interest in artifact SETI, the search for physical objects of extraterrestrial technological origin. Oumuamua sparked intense debate about whether interstellar visitors might be probes rather than natural objects. 3IR Atlas represents a different kind of test. Instead of speculating about unusual shapes or acceleration profiles, we have a specific, testable prediction. If the object can place fragments into orbit around Jupiter, despite the physics constraints we've discussed, that's not just unusual. That's diagnostic. It's a signature that natural processes cannot easily replicate. This contradicts what we previously thought was the best way to search for technological artifacts. Most proposals involve looking for artificial structures around distant stars, or listening for deliberate transmissions. But if technological civilizations send probes through the galaxy, then looking for anomalous behavior during close planetary encounters might be one of the most efficient detection methods available. We don't need to search a million stars. We just need to watch the objects that come to us. Of course, there's a significant chance nothing unusual will happen. 3I Atlas might pass Jupiter without incident, continuing on its trajectory until it fades from view. The non-gravitational acceleration might have a conventional explanation we simply haven't thought of yet. Science is full of mysteries that turn out to have mundane explanations. But the possibility remains that we're about to witness something unprecedented. And that's why March 16, 2026 is a date that everyone interested in astronomy, planetary science, or the search for extraterrestrial intelligence should have marked on their calendar. But Eupheme didn't show up alone. It's part of the Ananke group, a family of 15 Jovian satellites sharing remarkably similar orbital characteristics. They all orbit Jupiter retrograde, opposite to the planet's rotation. They all have highly eccentric orbits inclined at steep angles. These are not orderly orbits from moons that formed in place. These are the chaotic orbits of captured objects. Let's look closer at the data on how these captures work. The prevailing theory is that the Ananke group formed from the breakup of a single, larger parent body. Sometime in the distant past, a wandering asteroid or comet passed too close to Jupiter. The planet's gravity captured it, pulling it into an unstable orbit. Then, Through collision or tidal stresses, this parent body shattered. The largest fragment was named Ananke. The smaller pieces became the 14 other moons, including Eupheme. The retrograde orbits are key. The 4 large Galilean moons orbit prograde in Jupiter's equatorial plane. They formed from the disk that surrounded Jupiter billions of years ago. But Eupheme and its siblings orbit retrograde backwards. This strongly indicates they didn't form in place. They came from somewhere else and were captured. This contradicts what we previously thought about how common these captures are. Jupiter has 95 known moons, and the vast majority are small, irregular, captured objects like Eupheme. In 2000, we knew of about 17 Jovian moons. Today, 95. And there are likely many more waiting to be discovered, too faint for current telescopes. So, what does this actually mean for the 3I Atlas encounter? It means Jupiter is very good at capturing things. The planet's massive gravity creates opportunities for objects to be gravitationally ensnared. And the timing of 3I Atlas's approach, with Eupheme at its apojove just 52 days before closest passage, is starting to look less like random coincidence and more like an example of how these capture dynamics work. Here is the crucial detail. Eupheme's orbit takes it out to 27.7 million kilometers from Jupiter at apojove. That's well beyond the 30.46 million kilometers that 3I Atlas will be from Eupheme on March 17th. In other words, 3I Atlas will be passing through the region where Eupheme spends part of its orbit. The interstellar visitor is threading through the Ananke group's orbital territory. When 2 objects pass close in space, they exchange momentum. The gravitational interaction can alter both trajectories. Could 3I Atlas perturb Eupheme's orbit? Almost certainly, at least slightly. Given that Eupheme is already on a highly elliptical, loosely bound orbit, any perturbation could have long-term consequences. It might alter the orbital period, change eccentricity, or even destabilize the orbit entirely. But there's another possibility that's even more intriguing, the one that has astronomers preparing telescopes and spacecraft for intensive observations in March. What if 3I Atlas itself gets perturbed so that pieces of it end up in orbit around Jupiter? As we established with the 53.61 million kilometer approach distance, 3I Atlas will be just barely outside Jupiter's Hill radius. It's in a regime where capture is theoretically possible, and if the object were to fragment, if pieces broke off during the encounter, some could receive velocity kicks that put them into bound orbits around Jupiter. They could become new moons, additions to Jupiter's already extensive family.